Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. So, today is the last section of the mixing and agitation chapter that we will cover. So, in the previous classes of this particular topic, we have discussed about the introduction of mixing and agitation process, mechanism of solid mixing, that particulate solid or powder mixing, and mixing index, how we can define the uniformity in the mixing process, then mixers for dry powder and cohesive solids, and also the liquid mixing. In the liquid mixing, different flow patterns, how we can control them, and what are the kind of agitator that are used, what is the power requirement for a liquid mixing, how we can control the vortex formation, all such things we have discussed. And today we will just continue for the power requirement section a bit more. In the last class we have seen that for power requirement of Newtonian fluid, and if this is rotated inside a tank of baffled or unbaffled condition. So, what will be the power requirement and how the different power requirement can be related with the dimensionless parameters or dimensionless number. Those are based on the geometry of the geometry of the tank and also on the fluid properties. Now, this mixing or power requirement they depends on many factors. For example, that what will be the circulation inside a liquid, and what will be the the velocity, and what will be the viscosity of the fluid, density of the fluid, all those will have an important effect on that, right. So, we will see today that power requirement for non-Newtonian fluid. Now, the power input to a non-Newtonian liquid may be estimated based on the apparent viscosity. We know that for the non-Newtonian liquid we can express the shear stress and shear rate behavior by this factor, and again we can write them as k into gamma dot to the power n minus 1 into gamma dot, right. So, this is called the apparent viscosity. So, based on this apparent viscosity, because for the Newtonian fluid what we have done, that we have calculated Reynolds number and Froude number also. So, this Reynolds number and some power factor correlation we did, and those correlation empirically has been defined for different kind of geometry of the impeller, and that helped us to calculate the power in a particular mixing phenomena. Now, when we want to use this, so instead of the viscosity term that we have used in the Reynolds number, now we need to use the apparent viscosity. Okay. So, in non-Newtonian fluid, apparent viscosity varies with shear rate. So, then mu A, that is the apparent viscosity, is expressed as tau by gamma dot, that is equal to k into gamma average to the power n minus 1. So, Metzner and Otto relationship has been developed on that is NRE is equal to ideally rho f into n into dA square by mu A. Mu A is the apparent viscosity, dA square is the diameter of the agitator or impeller, rho f is the density of the fluid, n is the revolution per second of the impeller. Now, how we can write this as rho f into dA square by k into beta to the power n minus 1 and n to the power n minus 1, because here mu A is related to the apparent viscosity, this is related to the average shear rate gamma gamma average is the average shear rate, beta is a dimensionless shear rate constant. Okay. So, and n is the n to the power n minus 2. So, this n is the revolution and small n is the flow behavior index. So, if we put it that shear rate, we are putting the value of shear rate, and shear rate is expressed can be expressed as the velocity gradient. Okay. So, velocity by the distance in that. So, using that we are now getting that this expression rho f into d square by k into beta n minus 1 into n small n in minus 2, capital N to the power small n minus 2. So, power number formula is similar to that of Newtonian fluid that we have developed, only with some change, some modification we have done here because of the non-Newtonian fluid. So, here we can see that for power requirement of non-Newtonian fluid, here we have Reynolds number with respect to the apparent viscosity, and here we have power number P by rho into n cube into dA to the power 5. So, if we see the difference between Newtonian and non-Newtonian, there is a in the viscous region there is not much effect. In the transition layer actually we have some effect, and again in the when very high Reynolds number we can observe. So, there is the change is not that much prominent. Okay. So, for the non-Newtonian we are getting a lower power number in the transition region. This correlation has been developed for 6 blade flat agitator with disc. Now, correlation for density and viscosity of mixture. So, empirical relationship are available for both the density and the viscosity of binary mixture. So, what are these correlations? These correlations are available for both density and viscosity of the binary mixture. So, now we have seen that when the fluid is there, and for the Newtonian and non-Newtonian how the viscosity will be changing. Now, for the mixture how this density and viscosity can evolve, that we will see now. So, if we see this equation, that is density, the combined density of a mixture rho is equal to rho c into V c plus rho d into V d, where V is the volume fraction and the subscript c and d represent the continuous and dispersed phase respectively. So, the continuous phase density and volume plus the dispersed phase density multiplied with the volume fraction. So, volume fraction of both the case multiplied with the respective density of the continuous phase and dispersed phase will give the total density of the mixture. Now, for an unbaffled vessel and for baffled vessel, what will be the case? For unbaffled vessel, mu, that will be the combined viscosity will be viscosity of the continuous part to the power volume fraction into the viscosity of the dispersed phase to the power of the volume fraction. And for a baffled vessel, the relation has been developed as viscosity will be equal to viscosity of the continuous phase mu c by V c into 1 plus 1.5 mu d, that is the viscosity of the dispersed phase into V d volume fraction divided by mu c plus mu d. So, these two equations are for the unbaffled and baffled in case of the mixture. Now, we have a problem again. So, that is a pseudoplastic mixture. Pseudoplastic mixture, if you remember in our rheology class, we have seen that non-Newtonian can be straight away differentiated into pseudoplastic and dilatant. So, if this is Newtonian, this is pseudoplastic where n is less than 1. So, flow behavior index is less than 1. So, pseudoplastic mixture is prepared by mixing two liquids in the volumetric ratio of 60:39.9 along with 0.1% emulsion. Now, a 4 baffle agitation tank having 1.2 meter diameter with 6 blade turbine, that is 0.8 meter dia, rotating at 200 rpm revolution per minute, is used for agitation. A draft tube is installed to facilitate higher shear rate. Okay. So, we have seen this, that how the draft tube is helping to mix it properly. Consequently, power requirement increases 20% due to installment of draft tube. Calculate the total power requirement and use empirical relation for non-Newtonian 6 blade turbine, that is power number related with this equation, that is 0.4486 NRE to the power 0.4587. Okay. So, for empirical relation for non-Newtonian, 6 blade turbine, this is given, this is the power number. So, no power correlation earlier we have taken from the chart, here directly the relation has been given, we will use this one now. So, liquid A and liquid B, because we are dealing with a mixture which is a pseudoplastic mixture. Okay. So, liquid A and B. Now, continuous phase is A and dispersed phase is B. So, this is given, that is 8 is the value of K and 6 is the value of K in case of the dispersed phase. N is 0.63 and 1.3, 0.65 and 1.3. Okay. Density is for the continuous phase 959 kg per meter cube and for the dispersed phase 1050 kg per meter cube, and also gamma shear rate, average shear rate, gamma value or gamma dot, that is equal to 10 into n, where n is the revolution, n is actually we calculate in revolution per second, here it is given in rpm. So, we will change it, and then for the dispersed phase the average shear rate is 38 in dA by dt to the power 0.5. So, first we have converted the revolution per minute to second, that is 3.33 rps. Then for liquid A, since shear rate we need to calculate, average shear rate 10 n, that is 33.3, 10 into 3.33. So, 33.3 per second. So, then for liquid A we need to calculate mu c, that is the apparent viscosity. So, the formula was K into average shear rate to the power n minus 1. So, 8 into average shear rate 33.3 into 0.65 minus 1. So, 2.35 Pascal second, and that is the apparent viscosity of continuous phase. Similarly, for liquid B the shear rate is 38 into revolution per second into dA by dt to the power 0.5. So, n value is 3.33 and dA impeller to tank dia, the ratio is 0.8 by 1.2 to the power 0.5. So, finally, average shear rate is coming as 103.31 per second. Then the mixture apparent viscosity for the mixture we need to calculate. So, shear rate from the liquid B will give you the value of apparent viscosity of the dispersed material. So, K into gamma average n minus to the power n minus 1. So, this is coming 24.12 Pascal second. For the mixture, the formula is this, mu equal to mu c by V c into 1 plus 1.5 dispersed phase viscosity into volume fraction of dispersed phase divided by the viscosity of the continuous as well as the dispersed phase. These are apparent viscosity, remember this. So, putting all the value 2.35 by 0.6, 1 plus 1.5 into 24.12 into this volume fraction 0.6 by 2.35 plus 24.12. So, we are getting 6.05 Pascal second. Volume fraction, yeah, this was also given, volume fraction was given. So, so we are getting 6.05 Pascal second. And density is again we have to put in the formula. So, rho c V c plus rho d V d, that is equal to 0.6 into 9 into 0.6 into 959 plus 0.399 rho d into 1050. So, 994.4 kg per meter cube. Then our aim is to find the Reynolds number. Okay. So, putting this rho and mu, and in we know 3.33 revolution per second into d a square. So, we are getting the Reynolds number. It is coming only 350.3. So, empirical relation for non-Newtonian 6 blade turbine. Relation has been given this as Np equal to 0.4486 NRE to the power 0.4587. So, putting the value of NRE now, because this we have calculated, we will calculate what is Np, that is the power requirement. Np is the power number. So, from the power number we will calculate the power requirement, because the formula is power requirement P equal to Np into density of the combined of the mixture into N cube into dA to the power 5. So, this is coming Np is 6.59 into 994.4 into 3.33 cube into 0.8 to the power 5. So, finally, we are getting 79.29 kilowatt. Now, the next thing is scale up of agitator system. Now, since we have seen suppose in a laboratory scale a small liquid mixture or agitator when we are designing. So, once we have got all the shape factor and the parameters fluid parameters done, power requirement calculation is being done, then if we want to scale up this process for an industrial scale. So, what we should look for? First is we need to go by geometric similarity. So, geometric similarity means that a single ratio between small scale and large scale applies to every length dimension. I mean, what scale we are increasing one dimension, we will increase in the similar scale or similar factor increase for all other dimension. The next is that kinematic similarity, in that two geometrically similar unit have constant ratio of velocity at corresponding point along with similar flow pattern. So, when the similar flow pattern is existing, for example, the axial flow or radial flow, these are same and two geometrically similar, that means let us say both are round bottom tank having the same kind of same, let us say 6 blade flat disc impeller is attached to both of them and with a constant ratio of the velocity. So, kinematic similarity we can maintain to upscale it. Third is the dynamic similarity, that is all corresponding forces at counterpart location in two geometrical similar units bear a constant ratio. All corresponding forces at counterpart location in the two geometric similar units bears a constant ratio. So, putting that, the dynamic similarity can be assessed for the two systems. Okay. So, that means basically the corresponding forces we can see that those are equal in the different cases. So, for example, at the end of the impeller tip you have measured the velocity impeller velocity you know. So, what will be the fluid velocity at the tip that you have analyzed? Okay. For example, this will be your lab scale lab scale impeller dia. So, from this point, if what will be your velocity of the impeller, okay, and it has the radial and tangential direction. So, if we consider the velocity of the fluid, if you consider the velocity of the fluid, so that also you need to calculate that this should be similar when we have the large scale system. So, at this point if you want to analyze what will be the force, so this will be same for the other upscale version, okay. Or else if you for example, the any places you consider that either impeller tip or what is the in the draft tube section. So, all corresponding forces at the counterpart location in the two geometrical similar units bears the constant ratio. So, maintaining these cases we can upscale the systems. So, in that equal liquid motion we can maintain or equal suspension of the solid, that we can maintain. So, third is that equal rate of mass transfer. So, we can see that for making this dynamic similarity, we can go for this kind of systems like liquid motion we maintain, or we maintain the suspension concentration of solid that we are suspending and we want mixing them properly, that we can maintain, or equal rate of mass transfer, that also we can see or we can maintain by this dynamic similarity. So, these are the thing keeping in mind when we want to upscale these systems. So, scale up ratio if we follow, scale up ratio SR, that is equal to V2 by V1 to the power 1 by 3, H equal to D, H we know the liquid level height inside a tank and D is the vessel diameter, and using this SR all new dimensions are calculated. SR if this factor we are maintaining, so in this factor only we will upscale or downscale this. So, SR into dA1, that will be dA2, SR into J1, that will be J2, etc. So, thus we can maintain the similarity between them, and to determine the agitator speed, N2 will be N1 into 1 by SR to the power n, as the ratio of n changes with the power of n, power of small n. So, here we can also write N1 into 1 by SR is nothing but D1 by D2 to the power n, where n equal to 1 for liquid, for equal liquid motion n will be 1, that is pi D1 N1 equal to pi D2 N2, n will be 3 by 4 for equal suspension solid. Okay. This n, the factor n will be 3 by 4 for equal suspension solid, and n will be equal to 2 by 3 for equal rates of mass transfer, that is P1 by V1 equal to P2 by V2. Sorry, this will be rho, this will be actually rho, then only we can okay. So, these three are the cases how we can do the scale up for a agitator. So, in this case while doing scaling up, SR is V2 by V1. So, that means only the ratio of the volume in the second one divided by the first one. So, that is eventually the ratio of D2 by D1. So, therefore, we have used this one V2 by V1 nothing but D2 by D1 So, SR will be d2 by d1 to the power 1 by 3, and with that we can upscale this case based on this 3 parameter, where n equal to 1 for equal liquid motion, n equal to 3 by 4 for equal suspension of the solid, and n equal to 2 by 3 for equal rate of mass transfer. Now, condition of an existing agitation system is as follows. So, the condition given as tank dia dt is 1.83 meter, agitated dia dA that is equal to 0.61 meter, J1 which is the width of a baffle, that is 0.15 meter, N1 that is equal to 1.5 revolution per second, density 929 kg per meter cube, viscosity 0.01 Pascal second. Scale up the agitation system for volume 3 times the existing one for the following objective. So, this you can see will be very beneficial for those who want to work this in an industrial scale system, you want to upscale this. So, how we can solve this? This is the problem of a scale up based on equal liquid motion. So, first we will consider this case dt equal to height of the liquid level. So, dt equal to h V1 that is equal to 3.142 into 1.83, this is the dia of the tank Q divided by 4. So, 4.813 meter cube. Then V2 we need 3 times the existing volume. So, we have calculated that. Finally, SR will be V2 by V1 to the power 1 by 3. So, 1.442, this will be the value of SR, scale up ratio you can consider this. So, dA2, dA1 is known to us. So, with this factor we will change. So, dA2 will be SR into dA1, that is equal to 0.88 meter, J2 will be equal to SR into J1, that is equal to 0.216 meter. Okay. So, then N2 will be N1 into 1 by SR to the power n. For equal liquid motion we know n equal to 1, small n equal to, there are 3 cases: equal liquid motion, equal mass transfer and equal suspension. So, for all that this small n is defined, then N2 will be N1 into 1 by SR. So, 1.5 divided by 1.442, so 1.04 revolution per second. Reynolds number, that will be rho f into n dA square by mu. So, 929 into n is 1.04 into dA 0.8 to the power square, 0.8 square, this will be 0.88 because it has come 0.88 square by 0.01 viscosity. So, we are getting very high Reynolds number. So, it shows the turbulence region. Now, from the graph we look for the value of NP. So, this is the correlation for this power number with respect to NRE. So, we are getting a very high range somewhere here corresponding to the value of Reynolds number, we are getting a very high range, and that for this particular flat blade turbine which is showing by curve 1, we will straight away see what is the value of this number is coming. So, this number has been taken as 5 in P. So, 5 into 929 into 1.04 cube, that is value of revolution, and into 0.88 to the power 5. So, 2.757 kilowatt. So, this is how we can calculate the power requirement, and we can scale up also the process. So, here we will end the discussion related to the mixing. We have once again we can remember that we have covered the importance of mixing, and what is the case for a solid mixing, cohesive powder mixing, mixing index determination, then liquid mixing, different flow pattern, and the power requirement in liquid mixing for baffled and unbaffled tank, for Newtonian and non-Newtonian fluid, also for the different mix kind of, and also for the scale up of a system. Okay. So, we will stop here and we will continue with another chapter in the next class. Thank you.